Okay, we move up here, I guess. Thank you for the introduction. Also, thank you very much to the organizers for this wonderful meeting and for all the clear advice on how to get here and things like that. And thanks to Lajos for helping to organize me coming here. And since I knew you would be here, I wanted to talk about something to totally bore you. So I'll talk about some of our joint work. And this is on a class of new change point test statistics that we classify as being of rainy type, and I'll explain why we came up with that name throughout the talk. And this is also based on joint work with Lajos's current and favorite PhD student, Curtis Miller. And so maybe it's somewhat lucky that this is one of the early change point talks here, because this maybe serve as like somewhat of an introduction to change point, because the framework that I'll be in is extremely simple here, that most of the talk I'll be talking about the simple at most one change point model for scalar time series. So this is what I want to do, is introduce this very simple model and talk a little bit about the history of some test statistics that have been developed in order to address this problem, and which motivate basically why we consider this new test statistic, which is there in order to improve basically the power of these tests when you could have a change point that's potentially near the endpoints of the sample. So in that discussion, that'll bring up this rainy style test statistic. So I'll talk about sort of its theoretical properties and how it compares to other test statistics for this classical problem. And in the end, I'll illustrate this with an application to change points in linear regression models. So like I said, we're basically in the most classical change point framework, which is what we assume is that we have observations of the form xi. These are just scalars that follow a sort of measurement error model, okay, that they have some mean mu I plus a mean zero error term. And we're interested in the change point problem, which, okay, there's maybe a couple of different formulations of this, but one classical way to frame the problem is as a hypothesis testing problem, where we're interested in testing whether or not the means of these observations are homogeneous throughout the sample, or against the alternative, and the simplest possible alternative to this is there exists exactly at most one change point at which the means are homogeneous prior to this change point t star, and after the point t star the means change to a different value. And we're basically just interested in conducting a hypothesis test of this. Okay, so this is a very classical problem, and sort of the usual technique one would employ here in order to address this problem would say that if it wasn't for the fact that t star was unknown, then this would be a very simple statistical problem, which would be a two-sample problem. So if we knew what t star would be, okay, and maybe you could imagine that the errors are, say, independent identically distributed, we could think of this as being a two-sample problem. We do a two-sample test. Okay, and so this would motivate basically a lot of the classical procedures here, is that if the point t would be known where the change point would occur, then what we might apply would be something like a likelihood ratio test. Okay, and the likelihood ratio test would amount to considering, say, like the two-sample t-test, which is equivalent to rejecting for large values of this test statistic. So if the true change point would be t, for example, then this would be, the two-sample test would say that we should reject for, say, large and absolute values of this test statistic, which is just comparing the mean, the sample mean from the first t observations to the sample mean of the remaining observations, okay, and then rescaling it by the variance. So this is like the two-sample t test statistic, okay, so then since we don't know the change point, which possible change points, where the change point is, then a sensible thing to do is to just maximize this two-sample test over all candidate change points. And we would consider a test statistic of this form. Okay, and then in order to perform this hypothesis test to fix the level at alpha, then what we might do is reject if this test statistic, okay, the belief would be that this should be large if there is a change point in there, because at the point t, which matches with t star, then we know that the test is consistent for the difference in the means at that point. So this test statistic should be big if there is a change point, and so we would reject if this statistic is, say, bigger than its distribution under the null hypothesis. Okay, and if the errors, say, had a, say, -1,1 distribution, you could calculate the distribution under the null maybe exactly, but typically this would be totally intractable to determine what's the null distribution of this, and so what we might do instead is compare it to its asymptotic distribution under the null hypothesis. Okay, and so in order to discuss that, this is what I've done here, is that here I just rewrote, using a little simple algebra, you could see that this sort of t test statistic is equal to basically a weighted functional of the Q-sum process. So this is, here we have basically a weighting function depending on t, and then this is the partial sum up to t, and this is the scaled full sum. So we basically compare the partial sum up to t to the full sum, and the maximally selected t test statistic is equivalent to the maximally selected Q-sum with some weights. Okay, so now in order to derive basically this asymptotic distribution of the maximally selected t-test statistic then, what we would notice is that, okay, we see it just depends on the partial sum process, okay, and it's well known, okay, even under much more general assumptions than, say, IID errors, like you could have stationary process with some sort of weak dependent structure, for example, that the partial sum process is converging weakly, okay, to a Brownian motion, or a standard Wiener process, okay, scaled by some variance term, and therefore this Q-sum process is converging in distribution to a Brownian bridge. And therefore, if we would sort of apply then the continuous mapping theorem, if we would rescale by the variance this maximally selected t-test statistic, then this should in principle be converging to a random variable of this type. And this is where one sees maybe the issue of using just the maximally selected t-test statistic in the change point problem, is that this random variable is actually equal to infinity by the law of the iterated logarithm. Okay, so in some, that I was loosely speaking here, this test statistic, the maximally selected t-test will converge in probability to infinity under the null hypothesis. Okay, so this is sort of maybe theoretically unappealing, although even in the 80s there were a lot of folks in change point analysis who were just using this test statistic and comparing to the quantiles obtained by simulation. Of course, they were simulating infinity. But the rate at which this is diverging with respect to t is extremely slowly, so it's hard to tell that it's actually diverging. It's only diverging at rate sort of log t. Okay, but for theoretical reasons, then it's at least appealing to try to consider, well, how would we adjust this maximally selected t-test in order that the limiting distribution would be tractable? Okay, so some ideas to then adjust this Q-sum so that it has a limiting distribution would be, say, reweighting. So rather than using the weights that come out of the maximally selected t-test statistic, these weights, okay, we would consider a different set of weights where, so if I would take tau, this tau parameter here to be equal to 1/2, then we would just have the maximally selected t-test statistic. So I could take this tau parameter to be somewhat less than 1/2, and then the limiting distribution would be this random variable, which is actually well defined. Okay, so one option is you could reweight the Q-sum. Okay, another option, which is sort of similar, or maybe more distinct, is that you could trim the domain on which the maximally selected t-test is calculated. So if we would define a trimming parameter, say t sub t, okay, which a classical thing to do, say introduced maybe, I don't know if this is the first time, but introduced famously in this paper by Andrews in 1993, is you calculate the maximally selected t-test, but only you trim the values away from the endpoints. So if I would pick this trimming parameter theta, okay, a classical choice might be to set theta equal to 0.05, and so we basically take 5% off each end of the sample and only maximize in between. Okay, in this case, the limiting distribution is the supreme of a Brownian bridge on a restricted interval. Okay, and then sort of another approach was popularized by Lajos and Marie and Edith Gombe is to consider sort of an extreme value limiting distribution of this test statistic. So another option is to say that we know that this maximally selected t-test is diverging under the null hypothesis, but under a new renormalization, say we could pick a sequence AT and BT, two sequences AT and BT, such that if we renormalize the maximally selected Q-sum process, then it's converging to an extreme value distribution. Okay, so we could renormalize the maximally selected t-test. Okay, and there have been other versions of similar tests like this, say one by Ling in 2007 and Hidalgo and Seo that follow the same basic principle of just renormalizing the maximally selected t-test, and so that you get an extreme value limit. Okay, so when Lajos and I were writing a survey paper sort of about change point, and this is where we started to discuss basically what's the advantages of one of these test statistics over the others. And the obvious point is that it would seem to lie in how effective they are in finding change points that are in the endpoints of the sample, because this is kind of the reason why we're doing this renormalization, is that you would have some sort of effective test statistic towards the endpoints. So I wanted to sort of show you how these tests work if you would apply them to change point or data that has a change point somewhere towards the end of the sample. So just consider the following extremely simple simulation study. We generate 5,000 samples which have a change point. In case of the observations, they have a change point at the point t star, and the errors are just IID standard normal random variables. Okay, and we take the size of the change is delta, and we take a few sample sizes here increasing from 50 to 500. Okay, Okay, and I'll just do all of the tests that I just had before, where I compare these test statistics to their asymptotic distributions. I estimate the variance in a standard way using a kernel spectral density estimator. Okay, although in this case you could just use the sample variance, would be fine. Okay, and then I'll just make some power plots. Okay, what was the percentage of rejections of the null hypothesis as a function of delta? Okay, and so this is what we see here. Maybe I forgot to mention this before, but here I just define this AT when this trimming parameter, or when this reweighting parameter tau is equal to 0. This is sometimes called the standard Q-sum process. So AT is the standard Q-sum process. So these are those power plots for the standard Q-sum process, and just the sample size is increasing, going from this one up to the top one. Okay, and the change point in this case is located at a bounded point away from the endpoint. It's 5% into the sample. Okay, so you can see the power of the standard Q-sum. And if we compare this to some of the other techniques that are built to be sort of improved when you have a change point potentially near the end of the sample, so this is the reweighted Q-sum where I took the tau parameter to be 1/3. Okay, it's a little bit size inflated, but you can see the power is improved. Okay, then here is the Andrews test statistic, still a little bit more improvement. Okay, but also a little size inflated, and this is the Darling-Erdos style change point test. Okay, so maybe if you would calculate the size adjusted power, probably the best, at least what we said in the paper, would be the Darling-Erdos style test. So this had us wondering basically whether or not we could approve, say, some sort of optimality results about any of these test statistics in sort of a local sense, when you would allow the change point to converge towards the boundary, whether or not the power of any of these tests would be optimal. Okay, and so to visualize this, so now I imagine I take the change point, but it's sort of converging to the boundary. So instead of having the change point be a fixed distance away from the boundary, here I take the change point to be t to the 1/4. So it's very close to the boundary. There's like 3 observations on either side. Okay, and this is the standard Q-sum. This is the weighted Q-sum, the trimmed Q-sum, and the Darling-Erdos. So you can see that there's still maybe some optimality for the Darling-Erdos in the sense that as the sample size is increasing, okay, we're still getting sort of an inversion here that it's getting worse as the sample size is increasing. Okay, but compared to the other tests, it's somewhat better. Okay, but this, say, leads one to the question is, are any of these Q-sum variants sort of superior to each other, and whether or not there may exist a different method of reweighting and trimming the Q-sum process which would be better for change points that are getting close to the end of the sample. And so this was the idea that I think Lajos was inspired by some previous work by Rainey about the empirical process, but this was the idea of considering a potentially new test statistic, is rather than looking at, say, the standard Q-sum process, what we do here is we're basically just considering the difference between the sample means for a candidate change point t. And if classically speaking, if we would allow this trimming parameter to just be like sort of a fixed fraction of the sample, then what you would get here, say if you would look at this a statistic of this type, okay, say t, the trimming parameter t sub t to the 1/2 times dt, is you would get a similar asymptotic to what the Andrews has. But an idea that seemed to have not been explored before is what happens if you would let this trimming parameter converge to the boundary at a faster rate. So this is what we imagine now, is rather than the trimming parameter being proportional to the sample size, we allow the trimming parameter to basically converge to infinity slower than the sample size. Okay, but also converge to infinity. Okay, so now we're looking at trimming parameter. So it's sort of a more aggressive trimming scheme to the Q-sum process. Okay. And so what's the idea for this test? If we wanted to implement it, we could try the same thing as we did before, is compare it to its asymptotic null distribution. So in order to calculate its null distribution, we just make this sort of primitive assumption about the structure of the errors, which is basically saying that we have some rate in their weak approximation to a Wiener process. So this is sort of like a split invariance type principle, is if we take the sample and split it in half, and we look at the partial sum process from the first half of the sample and the partial sum process from the second half of this sample, we assume that both of those partial sum processes can be approximated by independent Wiener processes, okay, with some rate here. Okay, where this rate, okay, so this result would be, is well known, okay, if the errors would be IID, for example. This comes out of the big guns, say like the KMT theorem. If you would have more than, say, 2 moments, slightly more than 2 moments, then these results would hold. So you should sort of imagine this holds under very general weakly dependent. So if you assume a stationary process for the errors, this would hold under quite general weak dependence conditions. Okay, and so under this primitive condition then, then what we have for the asymptotic distribution of this new test statistic is that it follows sort of an unusual law, which is if we define this random variable xc to be the supremum of a Brownian motion over the unit interval, then this new test statistic, when normalized in this way, converges to the distribution of the maximum of two such independent random variables xc following this distribution. And this is sort of where the inspiration came from calling this a Rainey style test statistic, was that there was some papers, I think the first one is back in the 50s, of Rainey, where he was trying to improve the power of Kolmogorov-Smirnov type tests by, rather than calculating them over the entire, say, real line, he would look at some trimmed value, okay, say AT, and he would let those go to infinity and then reweight the empirical process on that part to try to get a better test, which is more powerful in the tails of the distribution. And this is where we have a similar thing here, is that we've sort of done a similar trimming scheme, which should give the change point test more power in the tails or in the endpoints of the interval. Okay, so this limiting distribution showed up in several papers of Rainey about empirical process. Okay, so if we compare, then this is the Darling-Erdos power plots again, and here we have the trimming is at the 5% of the sample, and this is this new Rainey style test statistic where again we're comparing to the null distribution. We see that, okay, in this case you had normal residuals. Okay, we see that the size is quite good. Okay, so this limit law seems to show up well in finite samples. We have lots of simulations in the paper to support that. And it has similar power in this case. But if you go to the more extreme, okay, change points occurring closer to the end of the sample, okay, here's the Darling-Erdos, and now this is the Rainey. In this case, where you're taking the trimming parameter to be log t. Okay, so it can improve upon change points that occur towards the end of the sample. How much? Oh, maybe I have 10 minutes? Oh, 5 minutes? Okay. Okay, so it can improve on the power when the change point is very close to the end of the sample. And to give one last sort of heuristic, or one last example of a very sort of extreme case, so here what we were looking at is all competing methods that we were discussing before. I wanted to show a couple of things with this picture, which is how the test behaves if you would have serial dependence. Of course, that would decrease the power. Okay, and here we have the change point very close to the end of the sample, and we're looking at a very highly dependent residual process. Okay, then this approach here is the new Rainey statistic with the logarithmic trimming. Okay, and then this next statistic was the statistic of Hidalgo and CO, and then this is the Darling-Erdos and the standard Q-sum. So you can see that there's some improvement over existing methods when you would have change points very close to the end of the sample. Okay. And one of the other things that we did in the paper was to extend these change point test statistics to lots of other practical situations, say testing for change point in linear regression models. So if we have observations which follow sort of a simple linear regression, okay, with some covariates yt, then maybe we're interested in testing for the homogeneity of the regression parameters. Okay, then if we devise a test based on the residuals, so we estimate the vector of coefficients using ordinary least squares, and then apply the same test statistic to the residuals, this is what I have here, then we can show that this satisfies the same asymptotic results. Okay, then I wanted to present this because this will be the example that I show in a second. So some things that I'm not discussing in detail here, well, I'll discuss them a little bit as I go through these points, but what are some of in the paper we study many other error distributions in the simulation analysis to try to illuminate what are the drawbacks of this test statistic. And I think for sort of the obvious thing that one might think of why this test statistic would be poor is if you're looking at this, if you would have this more aggressive trimming, at some point you're looking at averages of a very small number of the sample. And so you would think this test would be much less robust, more susceptible to outliers, especially if they would occur towards the end of the sample. And there's some truth to that, although I'd say like a good rule of thumb for the trimming parameter would be this is some value for which you could imagine the residuals reasonably. If I average the residuals with that value that reasonably is close to the CLT already, then it should work pretty well. But it is somewhat less robust to outliers. The choice of t sub t is somewhat arbitrary. Okay, we suggest a logarithm, which works well in lots of the simulations that we've done. Let's see, what else did I have here? Okay, and the other things in the paper that we didn't discuss is we also extend this to the vector valued scenario because you also have these sort of Gaussian approximations in that scenario, and nonlinear regression as well as generalized method of moments. Okay, and just as a brief application, So we considered applying this test statistic to evaluate for change points in a what's called a 5-factor model in finance, but this is really sort of a simple linear regression model in which we're regressing sort of the returns of some portfolio over the risk-free rate onto a bunch of other portfolios, like things like the full market return, the return of small stocks over big stocks, the return of high volume stocks over low volume stocks. Those are what comprise these sort of 5 covariates here, okay, plus an error. So we're testing for change points in the Fama-French 5-factor model. Okay, and so what we did is we considered a portfolio that was devised by, I think, French, and we looked at the data of this portfolio's returns over a period starting in the beginning of 2005 and going up till about October 2008, and we applied this to a growing piece of the sample where we start the sample, the right-hand endpoint in the sample starts at August 1st and then goes to October 31st. And so we add one data point to the sample and keep applying this retrospective change point. And of course, what we're expecting to see here is that contained in this part of the sample is when the Lehman Brothers collapsed. So we sort of expect a change point at that point. Okay, and we applied the test sort of in a standard way by estimating the variance using a standard kernel leg window estimator. And then what I've plotted here is basically this is the logarithm of the p-values of this test as a function of the right-hand endpoint of the sample starting in August and going up to the end of October. Okay, and this top value is the p-values coming from the logarithmically trimmed Rainey statistic. This is the Darling-Erdos, and these are 2 Q-sum variants. This is what you see here is that in this sort of practical example, the Rainey-style statistic is sort of more capable of detecting this change, this huge change, when it's very close to the endpoint of the sample. Okay. Yeah, so this is just a quick summary, but I don't know if that's necessary, so let me just thank you for your attention.
Any questions? So how powerful is the test if the change would occur then in the middle of the sample?
I meant to say that in the drawbacks. So this is one of the drawbacks is that if you would pick the trimming parameter to be sort of small, you lose power in the middle of the sample. So it really is like there's a big trade-off that you're doing there when you have this more aggressive trimming is that you're going to get more power in the end but lose in the middle. So it's kind of a no free lunch on that part.
You mentioned that briefly, I think, in your talk. So this parameter t_tau converges, has a limiting behavior, right? But there is a constant hidden there, right? It goes to 0 in some sense.
Yeah. So this is this condition here.
So in practice, that's what you discussed, I believe. But in practice, how do you choose that constant?
Yeah. So this like if we were using log t as a typical example, but of course, like any constant times log t would also satisfy this same rate.
Right, but
here.
this has a huge impact on the small sample behavior, I guess, right?
It could have a huge impact on the small sample. It's really like if you're trying to get a change point that could be close to the endpoint of the sample, in some sense you'd like to pick this to be as small as you possibly could.
Okay.
Yeah, but practically speaking, the choice of the constant there could very sensitive to that.
Right, thank you.
Yeah, first I'd like to thank Emmanuel for inviting me for this conference, also to this beautiful, I would say, town. And what a beautiful town this is, because coming from the flat land of Urbana-Champaign, Illinois, this looks like heaven to me. And when I was walking today, this morning to here, I was wondering, how people can get any work done here, I'll be sitting in the riverside, whole day. But as our first speaker, Professor Hines says, maybe you get some work done a rainy days like this, okay? So it's nice to be here. Okay, so this is a paper, it can be termed, what should I say, Stat 101. Very basic thing that I'm going to talk about that some of you or many of you, apply all the time. Okay, and again, coming at this age, everything is history to me, And this goes back to my student days at Australian National University, kind of early 1980s, before many of you were born. And I read kind of 3 papers. When you're a graduate student, you read all the papers very seriously. So the 3 papers I read very seriously, one was by Hal White. I got the discussion paper long before it was published, and then Richard Kent biometric paper, and then a paper which I'm going to talk more is David Pierce's paper in Annals of Statistics, 1982. Okay, so when I was reading these 3 papers, suddenly that time I thought, there are kind of connections that need to be explored, among all these papers, and how useful those, connection can be. So, but again, as it happens, I didn't do anything for so many years, like almost 40 years, and then more and more I find out, if you want to read or write papers, you need manpower. And as you get old, your manpower decreases, But I'm lucky. Where did you get this, the pointer, the red thing? You see the red thing? Oh, yeah, here it is. Oh, so faint. Yeah, okay, here it is. So I'm very lucky because I don't have just one man, I have 2 men, Osman and Suleiman. They are, they are just very recent PhD students, Again, they were born long after I got my PhD, okay? Never married, they didn't get married. They worked 24 hours. So, to put things together, they had been very helpful to me, And so that's what I said, if you want to write papers, get, people like, Osman and Suleiman. Okay, anyway, so what is the problem that we are going to talk about? It is the age-old problem of what we can call, this, in testing, whenever we have, in the Newman-Pearson framework, composite hypothesis, then we have this called nuisance parameter, okay? And just giving a history, all of you know this, the first attempt, I would say, it goes back to student, as you can second line. And basically, he was testing for mean when variance is the nuisance parameter, and he has a finite sample solution. And then then a lot of it was taken by Georgi Neyman in a series of papers, but spanned over many years. And then and particularly his last paper, the way he tackled the nuisance parameter problem is doing some kind of orthogonalization, like he orthogonalize the score of the test parameter or the indicator function of the test parameter over the indicator function of the nuisance parameter. Just orthogonalize, then get rid of them. Okay, so that's the Neyman approach. Okay, and again, this is by Basu, the same as famous D. Basu's theorem, and again he put the importance of taking account of nuisance parameter. Okay. Now the main thing I'm going to talk about, this paper called Pierce paper, okay? And it has a very simple problem. Oh, let me see, go close. Yeah, okay, yeah. I think I will be, loud enough. I may not need this. Okay. So suppose we have these statistics. When theta 0 is known, there is absolutely any problem, try to find out the variance, okay? The main problem is once you replace this, to have a theta 0 by some estimate. It could be MAD, it could be GMA, it could be some other estimator. Then how do you calculate the variance of this? hardly reference either in the statistics or in the econometrics literature. Okay, this paper is somehow kind of hidden or lost. Okay, but I think this is a very important note. It's a small paper, 4-page paper. Okay, so what is had a very neat formula that how to adjust the variance once you simply replace theta by some estimator. Okay, so that's the yes, paper. So I kind of just quickly go through this, and in this paper, what we do, we kind of just put everything in a simple way. Okay? Details are in the paper, and then you can get the result, much more nicer way. I mean, under little bit general conditions. Okay, and so let me just quickly talk about that. Okay, so that's what the Pierce formula is. Okay, try to find the asymptotic variance of this quantity. Once I know the variance of Ty when theta is low. Okay? Very simple problem. Okay. And then what I'm going to talk a little bit, not all of them, some of them, that in econometrics we have lots of tests. Okay. And if you go and read these papers, very famous, this is more statistics, David Cox test for knowledge hypothesis, and then Halwai information matrix space, and previously Darwin. Oh, I'm not loud enough. Oh, co-recording. Oh, right. Okay. Yeah. So I'll talk about something, because I was a little bit worried, what does my talk fit into this conference? Then I found out a lot of people mention this test for normality, which has been my livelihood, for a long time. Okay. So I'm happy to talk about that. Okay. And if you look at all of these papers, test statistics, there will be a huge appendix to find out the variance. Particularly look at Hal White, paper in Econometrica 1982. It is a 50-page paper, but 25-page in appendix. But it's a very rigorous paper, but he goes through a huge calculation to find out the asymptotic variance of information matrix. Okay, or any of them, Okay, so I'll maybe pick up one or two of them and talk about it. Okay, so that's the his framework, yes, framework, that, under mostly MLE or efficient, estimator, okay. But then what we do in this paper, we just, it's not a big deal, but, we kind of, do this under, QMLE setup. Again, it is coming from, Hal White's, idea of distribution and specification. Okay. Let me see. Okay, so now the way we'll talk, this is the standard notation we'll be using, likelihood, log likelihood function, and then you forget about all those, and then the information matrix, and then, the standard stuff. Okay, this is standard. Okay, now what we are talking about, how to find the variance of this quantity. Okay, and the way we can start, suppose I have suppose this is MLE, okay, under this is the MLE setting, okay. Then, so this is the information matrix, and then the variance of this, after we replace theta by theta hat, look at the original variance is this, see theta 0, okay, when theta is known, okay, and most of the time this is trivial, I'll show you simple examples, this is trivial. Now the question is, what happens to the variance of t theta when replaced by theta hat? It variance is, the original variance minus something, okay? And that something is completely controlled by this, gradient, derivative of the test statistics with respect to theta, okay? And this is a very neat formula, okay? And that means you don't need any adjustment whenever this is 0. And there's a lot of nice interpretation of this, I'll talk about this, okay? And this could be proved in a nice way, and then that's what in the paper. So I won't go through this. Okay? It's easy. And in some sense, the proof is basically can come from here easily. So these are test statistics. So expected value of this is 0. This is the efficient estimator. That means when ML is efficient, then of course covariance between this and is 0. And that's why you get into this formula. Okay? And okay, so let me just forget about this. Okay, and again, this is another approach, but doesn't matter. Okay, now let me go back to this, standard that I started my, academic career doing this. That was back in 1979. Oh, exactly 40 years back. Okay, so we are doing this test, and then the test statistics, of course, just think about the skewness test. Okay, this is the test statistics will be this I can call it like an indicator function. That means so I use this let's call OLS residuals. Now when the parameters are known, and we know the variance of this is simple. You do we teach this first stat class 101 class. So the variance of this skewness when parameters are known is 15. Okay. Now the question is, once you replace those things by OLS residual, or what happened? Okay. Then the variance becomes, as I said in the Pierce formula, 15 minus that quantity. Remember this D and the information matrix inverse, and then the D, and that becomes the 6. Okay. So it's very easy to get, just using it like a few lines. Okay. And then exactly same thing you can look at, the kurtosis. When parameters are known, variance is 96 of the fourth moment. And once you use this, the variance decreases to 24, and this is the adjustment. It's coming from the Pierce formula. Okay, and that's what I got it, this jingle bell statistics, and somehow it became very popular. It was originally done, long time back, 1979, but it took a long time to get it published, the original paper. Anyway, so this is the test statistic we have, 6 over n, 24 over n. Okay, and when I was doing this, I just used this call, Pearson family, and then standard Rao score test. Okay, I didn't have to go through this calculation of 6 by n, 24 by n. Okay, what happened? It just came out of the whole exercise of Rao score test. Okay, and when I was doing this, then I found the variance of skewness is 6 and variance of kurtosis is 24. I was a little bit puzzled, but I just thought there is something wrong. But since it came from Rao formula, I said this must be right. Okay, but that time I have no idea back in 79 that where does this come from. No, I thought it's 15, and I thought this is like much larger than 24. But now, after reading the PS paper, I knew that what's really where does this number come from. So in a way, it's counterintuitive that your variance decreases when you replace the parameters by its say MLE or some estimator. Okay. Okay, so that is the thing. Okay, and then as I said, in econometrics we have so many different tests, and all these papers. I mean, there is nothing new here, but what basically I'm trying to say that all these are like a Cox test. It's a very complex test statistics. Look at this. You have two different model, non-nested model. You want to test. Then you have this very complex test statistics like this, and then you don't know the parameter delta. Delta is this kind of parameter, which is coming from the both, two different models that you want to test against each other. And this is complex. And of course, the Cox has, a few page derivation to find out the variance. But if you apply the, the Pierce formula, it is just few lines. Okay, you get the test statistics, Okay, same thing. Okay, that will be information matrix text. Again, you can see the test statistics is composed of this, two estimates of the information, and then again, variance is complex, But again, if you apply the Pierce formula, you just get it, in few lines. Okay, as you can see that, Okay, we can just calculate the variance, Okay, and so in this case, let me just go back, just a little bit here, because I'll be going to use that. Okay, yeah. Look at this one, the original test statistics. So this is our MLE setup. This is our test statistics. Now look at, for under this MLE setup, the covariance between our MLE or any efficient estimator and the test statistics is always 0. Okay, for the, when I am looking at the MLE setup. Okay. So we'll see what happens to that in a little general conditions. Okay. Okay. So what I'm trying to say that there may be a lot of statistics that can be simplified their variance calculation using the Pierce approach. Or anytime you would kind of suggest a new test or come up with a new test, I think Pierce formula will be very useful to find out the asymptotic variance. And also, and again I'm saying this repeatedly because I have not seen, there is very few, 2 or 3 reference, except myself refer to or citation to Pierce paper. Okay, I don't know why people do that, but okay. Anyway, so these are all those examples. Okay, so let me just same as Darwin-Age test. See, Darwin-Age is kind of it was in 60s people are all using Darwin-Watson test, and then they knew that the test is not good. Okay, Darwin-Watson test because of this variance formula. See, variance of this autocorrelation estimate is basically 1 under the null. Okay. But that is when you know the parameters, the regression parameters. Okay? But if you use again, Darwin derived the whole thing in a completely different way. But if you use Davis, just 2 lines, the variance is not 1. It is 1 minus something because you have estimated a parameter, beta 1. Okay? So you can see everything, very much more clearly. Okay. Now let us think about the QMLE setup. Okay? And, so that the assumed density F is not right. That may be something else. We call, I think, call G. Okay. And then we, we put some another information matrix based on the outer product. And then, as we know, that under QMLE setup, that you don't have any 2 parameter. You just have pseudo 2 parameters called theta star, which minimizes the Kullback-Leibler information. And then you have this distribution. Okay. Now, again, little bit of history. And there is a lot of debate, who did this first. Statisticians argue this is done by Eker and Hoover. Econometricians say it is White. Okay. The answer is none of them. The whole proof is in this, long back 1950 Cowley's Convention monograph. It is not the result. They have the whole proof is there. Okay, so when you talk about the sandwich estimator, this is the paper I think we should be talking about. Okay, anyway, so that with that change we can do the exactly same thing. I can go through this. Now what happened? The result changes to this. Remember earlier we had this. Now I don't have 1 information matrix, but we have. So we will be talking about the sandwich formula. Okay. Now the result changes. Very similar. Now theta hat has a variance, the sandwich, the QMLE, and this is my test statistics. Now it variance is S theta star. And you can see S theta star is a little bit complex expression. And now also look at this off diagonal part is not 0. Because in terms of QMLE, the covariance between the whatever the QMLE and your test statistics is not 0, and that depends on this quantity. And in MLE setup, this is 0. Okay, and as you can see that everything of course boils down to previous result. If our assumed density F is same as the assumed density, the true density Z. Okay. 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 So let me log. Okay. Now if I want to go back to the the skewness statistics where we have misspecification, then let me see whether I can do that. Okay. And now suppose I want to test for only skewness. Okay. The JB test we said it is under the joint test, skewness and kurtosis. Suppose I want to test only skewness. That means we don't assume anything about the kurtosis parameter. Then what happens, as you can see, that the sandwich part will involve, under skew null, thus the kurtosis part. Okay, and then if you look at the variance, ultimately, earlier it was, remember, it was 6, but now it will be no longer 6. It will be this, but again, if you put mu3 is equal to 0, some of them will be 0, but still you will have all those, extra, what do you call, the fourth moment, values. Okay. So that's again, just come from just adjusted, the Pierce formula. Okay. And again, you can do this, for kurtosis and all those things, Okay. Okay. And so, and what I think this is a kind of, we are just at there, and what we have done recently, that you can kind of, so we go from MLE framework to QMLE, and then you can easily go to this kind of, okay. When you estimate, in GMM or some other, the empirical likelihood method, then the variance formula again changes depending on your estimation method. Okay. How much time I have? Oh, very good. Okay. Yeah. And so anyway, so we can do that. Okay. But there is another thing, as you might be already guessing, there is another formula that we use for variance estimation, what is known as the delta method. Okay. In first year econometrics class we teach, and all the statistics textbook and the econometrics textbook had this call, the delta method. Okay. It's very close to Pierce, but not same as Pierce. And as, like myself, I know I was looking at the history of delta method. If you go back to your statistics textbook, you will not find a single reference to delta method. It's just called delta method, as if it has been there, from the beginning of statistics. No, there is absolutely no reference to the delta method. Okay. So I am in the process of writing something called a complete history of delta method, although there is no history. Okay. And it is very similar to this, but it's not exactly the same. How to find the variance of a, if it's linear, no problem. More in the case of delta method, mostly used in the non-linear case. Okay. And what happens, this delta method, pair method, sometimes they can give you different result. Okay. So that's what kind of, still try to, trying to see how the Pierce method, kind of, connect. There is definitely a connection. So we are still working on that, finding the, okay. But again, delta method is little bit different. There is no question of nuisance parameter at all. There is absolutely no concept of nuisance parameter. Just suppose you know the variance of theta hat, then what is the variance of g theta hat? That's the whole delta method. It's a simple, one-line formula. Okay, but Pierce is different. Okay, but they lead to most cases the same result. Okay, so now that what we are doing, along with this GMM or any kind of estimation, how the variance adjustment took place, first thing. Second thing, how Pierce method is connected with the delta method, and how they differ or they don't differ. Okay, so that's what we are up there right now. Thank you. Okay, maybe I should say this. Any questions? Okay. Sure.
Next speaker is Professor Lajos Horvat.
So, okay. Is it working or? Okay. So, thank you very much for the invitation. It is my pleasure to attend the second of these goodness of it meetings there. So, this was essentially a joint work with Piotr Kokoschka, who is supposed to be on his way to his meeting. We haven't heard from him for days, but he's coming. This is the claim. The third author is Jeremy Vanderdas, and he's a master's student at the University of Utah in electrical engineering. So he finished his electrical engineering project, but they were still paying for taking classes, so he decided that he will take something which is more interesting than electrical engineering, like taking measure theory-based probability and numerical mathematics there. And this is, I would say, is a typical American project. All of us are US citizens. None of us were born in the United States. So Jeremy is a very industrious student. I think he was born in Amsterdam, in the Netherlands there. So let's look at, okay, what the model is. Okay, so we have essentially n functional observations. Those are defined on some interval there. If you look at this one here, okay, so we have like xit is a linear combination of some functions there plus an error term there. This is called the dynamic model because when you are looking at the coefficients, those coefficients are random variables there, yeah? So there is essentially a constant term there, the c's, plus you are looking at an error term there, and this is the reason, okay, why this is called a dynamic model there. If you look at this one here, when you are computing the expected value of those observations, okay, at least what we are looking at here, okay, if this model is correct, then in this case, those are the linear combination of k functions there. Okay, now, the basic assumptions is the following there, okay, the first one, what I said, that the expected value of the observations can be written as a linear combination of those functions there. When you are looking at the functions, those are assumed to be known. And I will discuss this one a little bit later on. The interesting thing is, okay, so you have these coefficients, the c's there. Okay, if you look at this one, it is essentially a linear model with respect to those. So they are not overwhelmingly exciting, okay. The most more exciting is essentially the lambda naught, which is sitting inside, okay, of those functions f there. Usually in the applications, what we have seen so far, and this is coming from economics there, it is assumed that lambda naught, this is a given number there, yeah? And when you start making inquiries where it is coming from, nobody really would like to make a comment about that one here, okay? So if you are looking at different papers there, the value is changing a little bit there, but it says, okay, that it's coming from previous experience there or like doing experiments and things like that one here. So essentially, if you think about this one here, since you are not really estimating, okay, the parameter lambda naught, essentially, okay, this fkt lambda naught, this is treated as some kind of a given deterministic function there. Okay. Now, there is an interesting comment about that one here, okay, and this is coming from Moscovich, and this is an interesting paper, okay, about investing there. Only thing what I did, I rearranged. If you look at this one here, 1 and 2 there, okay, so essentially that you have this linear combination, plus you have those additional error terms there. If you are looking at this one here, when you are looking at the model, you will see that you have the first term here when you have the mean there. Then when you start, okay, with the error terms there, when you are looking at the f terms multiplied with random variables plus the epsilon it there. So in this case, okay, if you assume that, for example, this function df, those are orthogonal and the corresponding error terms are uncorrelated there, then in this case what you can see in some sense that when you start the Karhunen-Loew type expansion of the function there, you are using essentially, okay, the same functions for the mean there, and also you are using essentially the same function for the error terms there. Yeah? So in this case, okay, so idea is, okay, which was pointed out by Moskowitz there, that maybe if you are looking at this one here, when you are trying to do projections there, okay, he is using projection to derive optimal investment portfolios there, instead of using just purely, okay, the covariance function there, we would like to try some kind of a linear combination of the covariance function, okay, and also to include the mean functions there. Yeah? It's very, very easy to see that essentially you can have situations there when the eigenfunctions of the covariance operator might be orthogonal for the mean there. Yeah? So in this case, if you are using projection there, the mean in this case is completely out. Yeah? This one showed up, I would say, since functional data analysis started there. The best comment came from Peter Hall. Okay, when this issue was raised to him, he wrote in the Annals of Statistics that God is not that mean. Okay, so Moskowitz, would like to make money. He doesn't really trust God. Okay, that it will not be mean to him. So he suggested something like this one here. In his paper, there are a few studies there when they do the simulations there. Interestingly, C.2, this is which work better. And in this case, essentially, the profits what they made, it is increased between 2 and 10%. Okay? I assume that this is not too much. In statistics, 10% is negligible. It turned out, okay, in finance, okay, 10% is a major, major improvement, okay, what you can do there. So this is a comment, okay, about this one here, that essentially, if you look at the model in a way like this one here, you can imagine that who wrote up, okay, this dynamic Nelson-Siegel model, they tried to explain essentially the mean and also variability in the data there with the same function there. There are a few examples for that one. The first one is the original Nelson and Siegel model there. If you look at this one here, there is a base function there. Okay, this is the level. And in this case, you are looking at the slope and the curvature there. Roughly speaking, okay, that you have there the function 1 there. Then you are looking at, okay, the exponential function and in some sense the derivative of f2 there. Okay. Now, the claim was that if you are looking at this one here and you are trying to this one here to the US interest rate curves there, then in this case, okay, it doesn't explain some kind of a bump at the beginning of the data there. So additional function was introduced there with an additional parameter there. So in this case, now the lambda naught is bivariate. And if you are looking at this one here, now we are looking at, okay, 4 functional observations, four functions there. Sometimes, okay, those are the so-called functional factors there. Then more is coming up. Essentially, it was criticized that if you are looking at the model example 1 and example 2, then it is not arbitrage free there. So this means that when you are looking at the factors there, those are just not enough to make this one for an arbitrage free model there. So therefore, additional terms were added to this one here, okay? And in this case, when you are looking at this one, it is essentially, now this is an arbitrage-free model there. And if you look at this one here, you are looking at 5 functional observations there. Okay, the Fama-French model, which was used by Greg, is again used as a motivation why, in some sense, the 5 is the best one. Yeah? And we will see later on that this is absolutely incorrect. Okay, there is essentially 2 additional ones which were suggested in the literature there. One of them is the polynomials there, and this is essentially not the interest rate yield curves there, but the zero coupon yield curves there. Just an example, okay, that instead of the exponential function, others use polynomials there. The last one here is a very, very simple model there. This is an exponential model when essentially you are looking at a series of exponential functions, and essentially, okay, this was used by the Bank of Canada, okay, to estimate yield curves on Canadian bonds there. Okay, so they said it's working very well if k is large. Okay, so if you go back, okay, what they did there, k is large for them means that this is 15. Yeah? If you think about this one here, okay, that like the original model, we start with 3, and now you are going back to 15. Yeah? Is essentially getting worse and worse there. In case of 15, okay, so the number of the parameters is getting larger, so essentially it may not be the best for this one. Now, how to estimate the parameters there? Okay, so essentially what we are interested, we are looking at, okay, those, I cannot really see the dot, yeah? Okay, you are looking at essentially the parameters, you have the C's and the lambdas there. When you have the true value of the parameter, you put the 0 there. What I suggested is essentially using the least squares. Originally, there was no measure there, and after when we started doing the simulations, and in this case it turned out that using essentially a weight function there, it makes everything much, much better. Essentially, when you are looking at, okay, the data what we have, and this is essential data provided by the Federal Reserve there. Okay. Okay, Jeremy is one of my very first graduate students who got a job for me. So it turned out that during the summer, when we were corresponding, essentially I was working for Goldman & Sachs, because it turned out he became an intern, and Goldman & Sachs was deeply interested in a project like that one here. So it turned out how to work with interest rate curves there. It was very, very important for them, and in this case, okay, came this function like that one here. So if you think about this one here, okay, this is now a standard problem there. In some sense, you are written up some kind of functional form there. If you compute the integrals, then in this case, okay, you go back, okay, what you have done, and you have some before there. The standard assumption is, okay, that first of all, you assume that MT is a non-decreasing function on this interval there. There are two cases, okay, what we looked at, when MT was essentially a function increasing by jumps there, and very, very smooth between the jumps. And the other one, okay, was essentially a relatively smooth function like the Lebesgue measure, or the function 1 divided by t there. The next assumption is standard. Okay, we are maximizing on a compact set there. This is mainly assumed that we can use the classical theory there. Okay. Then, further assumptions like this one here, okay, to make everything very, very nice and very simple, it is assumed, okay, that the function, okay, FLT lambda, this is a smooth function with respect to lambda there. Okay, so it's essentially Lipschitz continuous there. The next one, okay, so what is assumed that you are looking at, okay, is the set there when these two functions are the same, and in this case, okay, that if the measure of this one MT is 0 there, then in this case, this should uniquely, okay, determine the values of the parameters there. Okay. The proof is based on the book of Van Zangel, so in this case we are just trying to establish some kind of an assumptions that we can use, in some sense, his method and his result like that one. Okay, so here comes essentially the interesting part there. Yeah? When we are looking at the volatility there, so this means that when we are looking at the distribution of those random variables, stationarity is not assumed anymore there. Yeah? So in this case, essentially, there are times that during the observation period when the second order property may have changed there. Yeah? So essentially, you are looking at certain intervals there. We do not know when those intervals start and where they end there. those are stationary on those intervals, but not necessarily they are stationary on the whole observation period there. Yeah? Model like this one here was used in a paper by Bartley and other people there. Again, they looked at the same type of data there, and this was observed from the beginning, that the second order property, okay, it may not be stationary there. In this case, the data was segmented using essentially the meetings of the Federal Reserve, or there was some kind of a very important announcement which may have caused, okay, some kind of a change in the second order behavior of this type of observations there. In this case, we do not assume that those times are known there. It can be the whole sequence, okay, is a stationary sequence there. It can happen that it is essentially changing a few unknown times there. The next assumption here, okay, what do you mean by stationarity there? And we are just following, okay, the standard assumptions there. When you have essentially the interval of stationarity, that in this case, those observations can be modeled as Bernoulli shifts there. Yeah? So if you look at this one here, it says that you are computing, okay, these error terms there. So this means that, okay, the k random variables and the function there as some kind of, in some way, in a similar way computed from IID random variables and some kind of a space there. The assumption is that those can be in some sense approximated with v-dependent random variables there. So this means that in some sense, okay, what is happening, like at the very, very end of the data, it doesn't matter too much there. Yep. Okay, so it's essential assumption what we are using there. Okay. Now, if we assume those previous conditions, then in this case, okay, so we have consistency. So this means that the estimator is converging, okay, to the true value of the parameter there. Okay? I said, okay, that the proof of this one is somewhat technical, but as I will say, okay, that whoever read the book of Professor von Zangel, okay, then in this case, he can follow the arguments like that one. So, okay. The same thing is done there. The next question is the asymptotic normality, how to get this one here. There are a few assumptions, okay, concerning values of these m functions there. So it's essentially inside of the L, we have the lambda there. Certainly, if we are looking at something, okay, which is smooth with respect to the parameter there, so we introduce the derivatives of those functions, okay, with respect to lambda there. The next thing, okay, what we have, we would like to write it down, essentially, the structure of the limiting Gaussian process there. And this is the reason, essentially, okay, so when you have those functions there, if you write it, those essentially functions and covariances there, because essentially, if you are looking at the covariances on those interval of stationarity, you may get different type of values there. So when essentially the whole data would be stationary, then in this case you would have one like di here, or you only would like to have some kind of a one single, okay, dit there, okay, but in general, okay, this is missing there, unfortunately, okay, this should be dist and also, okay, dits in the last line there. So in this case, explicitly, you can write it down. What is the covariance structure, okay, of the limiting Gaussian process there? It is essentially nice and close for. None of the functions what you have are known, and none of them can be computed there. Yeah? Because essentially, you do not know the values of these key i's there. Yeah? Those are completely unknown. This makes essentially the resampling nearly impossible to do it, okay, because whatever method you would like to use, any kind of bootstrap for dependent data there, some kind of a station use here and there, yeah? But it's essentially not there anymore like there. Okay. So, a little bit more assumption that is about the rate of the approximation. you need a little bit more than for the consistency there. Again, the result is not a very, very shocking one. It tells you that your estimator, this is asymptotically normal. The limit distribution is written down in terms of the Gaussian process, which was defined via its covariance structure on the previous slides there. Okay. This one here is, of course, normally distributed there, just because it is an integral of a Gaussian process, and even you can write it down, okay, how the covariance looks like. This is theory. I would say this is not really useful when you would like to do any kind of statistical inference. The next one, okay, what we looked at, this one here, okay, like how to test if this model is correct. Yeah? Okay. The problem with the Nelson-Ziegel model is, if you look at those exponential functions like this one here, it is used even when the data is not necessarily intersect like that one. So it was used, for example, to model commodity prices. The assumption is, okay, of course, like, okay, so you have a contract instead of 10 years for 30 years, then in this case, probably in 30 years, you need to pay more. Yeah? So essentially, they are assumptions like this one here, even if used modeling like this one. This is an interesting question, okay, whether it will work or not there. Yeah? We can use this still exponential function, whatever was suggested there. Okay, so how to do and how to apply this theorem there. There is an outline of that one here briefly. We worked with the L2 distance there, okay? The reason for this one here, that working with the L2 norm is very, very nice and very, very simple, because in this case, essentially, you can use the Carhunen-Loewe expansion there. Yeah? So in this case, CTS, this is the covariance structure or covariance function of the limiting process there. If you compute the eigenvalues, eigenfunctions, that in this case you can write it down the distribution of the square integral of the limit. This is essentially just a weighted sum of the squares of independent standard normal random variables there. So the only question is that, okay, how to get those eigenvalues there. And this is relatively simple as long as you can estimate from the sample the covariance function there. Then in this case, you can use those empirical eigenvalues there to approximate, okay, this infinite sum there. Yeah? So essentially, the only problem what you need to solve now, how to estimate the covariance function there. Yeah? And the rest of it is like numerics, okay, how to get those eigenvalues like that one here. The interesting part is that if you are looking at the standard method, okay, just essentially just using the weighted sum of the correlations there, even in this case is working there. The typical proof of this one here, that you have stationary data and you show that Cn hat Ts in L2 sense is converging, okay, CTS like this one here, because what we have here in some sense, okay, interval stationary, then in this case you will have, okay, this L2 consistency there. Yeah? You have the L2 consistency there, and in this case, okay, this is a standard fact from functional analysis that you have a similar relation between the empirical and the theoretical eigenvalues like that one. Okay. So in this case, you can get the critical values there. The only thing is, in some sense, this is empirical if this is working out there. Okay, so far I said that this is working under the null hypothesis. What happens under the alternative there? If you look at, okay, what you have, we have the alternative that essentially, okay, the fit is not good there. Then in this case, when you are looking at the integral Cn square, which was converging to a limit under the null, now this increasing like n like that one here. What you can show in this case that even the Cn hat in this case, the estimator of the covariance structure there, which is not really there anymore, okay? that your estimator cannot increase faster than the square root of h. H is a window which is showing up in the estimation there. Then in this case, you have a similar order for the eigenvalues like this one. So the eigenvalue is still going to infinity there, but slower than n there. Yeah, because the assumption is h divided by n. So this means that under the null hypothesis, you have the right level there, and under the alternative, essentially, if the sample size is large enough, you will reject. Okay. So these are the US interest rates for 5 days there. If you look at this one here, okay, in the beginning, the data is relatively dense. You have 1 day, 2 days, and so on. At the end, essentially, you are looking at 20 and 30 years like that one here. Okay? This is the same thing. Essentially, these are not lines, but essentially, these are curves there. Okay? But now they push together like that one. Okay, this is the same version of that one here. Is essentially when you are looking at like some kind of a different type of picture there. Okay. So this is the data what we used. Okay, that. We are looking at maturities, and these are, okay, given in essentially, okay, days there. So this means that the last one is essentially, no, it's given in months there, okay, so the last one is, okay, 360 months there, so it's essentially 30 years. Yeah? Okay. If you look at, say, this one here, the interesting thing is that these are not equally spaced. Data there, you have much more at the beginning, very, very close to each other, and you are looking at, okay, the last 3 observations, the gap between them is relatively large. Yeah? Okay. Then, everything is transformed into the 0-1 interval there. The weight what we are using is the Lebesgue measure, and the other one is a jump which has jump at, is essentially at the time of the maturities there. Yeah? So only thing is used to estimate the curve, essentially when you have observations like that one. And the last one is the function 1 divided by t. So these are essentially how they look like. These maturities there, I would say these are relatively closer what we have here. This is another period there, so you can see that the structure is somewhat different. Yeah? Not exactly like this one. Essentially, maybe the volatility is really changing there. Okay. So this one here is an estimation, okay, and this is done using essentially those 25 data which was available on January 219. If you look at this one here, okay, this is the curve which is fitted to it. Essentially, this is the constant. Yeah? Okay? I would say, okay, when you look at this one here, it doesn't look very, very good. Yeah? When you are looking at this one here, okay, that this is not like 1 point there, because essentially, okay, all those 25 points there. Yeah? Okay, on that one. Then in this case, this is essentially what we are getting. If you are using essentially the weight function which has jumps at the times of the maturities there. Yeah? And in this case, it's way, way better. Essentially gets much, much better, okay, what we have at the beginning of the data there. Okay, now, this is an experiment there. If you look at this one here, okay, you are looking at when you are using the weight function, and we are looking at the 3-factor and the 4-factor model. As you can see, the difference between them is very, very small. Yeah? So if you are looking at essentially the differences, okay, these are essentially negligible there. Okay, this is even better there. You have larger volatility. So even in this case, the fit is much, much better in the sense that the 3-factor and the 4-factor are essentially the same. This is the differences like this one you see as 10 to minus 5 there. So when we worked on this one here, okay, where is that one here? Jeremy continuously went back to that one. So we couldn't answer this with Piotr, why the hell he's interested in the method, which is completely bad. It turned out, okay, when Goldman and Sachs is providing loans there, okay, they very, very rarely will provide consumer loans for, I would say, 3, 4, 5 months there, yeah? So when you talk about, okay, cars, those are between 3 and 5 years, houses like, okay, 20, yeah? And again, when they would expire there, those are not exactly round numbers there. In a lot of cases, like how much people need to pay in a given month, this is fixed like that one, yeah? So Goldman and Sachs had the data there, but instead of the beginning, they had much more observations at the end like that one here, yeah? So in this case, it's essentially not using the weight function as we use there. It's way, way better there, because in this case, it puts much, much weight, okay? Whatever you have at the end of the data there, yeah? If you look at this one here, that essentially the weight what you put on the last 2 points there, the combined weight is exactly what you have at the beginning of the data there, even less. So in this case, not surprisingly, if the fit is not better. So thank you very much. So sorry about the additional 2 minutes. What are you?
Any questions? Comments?
Well, this were too small, at least for me. It was too small. I could hardly read it.
Oh, we couldn't make it larger. We would have said, okay, we would have magnified it, okay, and to have it larger. Yeah.
Any other questions? Okay. The next speaker is Professor Bosch.
First of all, thanks to the organizers and in particular Emmanuel for inviting. So, thank you very much for your hospitality so far. So this is joint work with a master's student of mine, and partially, and I of course give additional thing. So the topic is about, as it says, exceedance location. So we are in a spatial context, so we have observations on a spatial grid, and we want to know where the mean is larger or lower, smaller than some threshold. And of course it has examples, important examples. This is downloaded from NASA. You can get such a picture if you just go there. And we're not, in this talk, not analyzing, this is total column ozone plotted. And we are not analyzing that in this paper, but just to show that this is a non-exceedance example. And we are not going to talk about it, but I'm talking about it nevertheless because it's such an important thing. So this blue patch here, the blue patch here is where the ozone level is lower than a threshold, this 220 Dobson unit that was apparently observed never after 1979. So anything below that is considered alarming. This is another data set, something completely different. Here's an exceedance example. So this is from forestry. That's a part of Alaska. The red dots are where they have tree data, tree diameter data. And so question might be for the foresters, where are the thick trees? So in a large database, we'd like to have some automatic procedure. So we look at it in a non-parametric regression context. So is this equation in the middle here, y is equal to mu plus epsilon. And just to explain the notations quickly, so y is observed, yi is y at S of I, that's up there. So S of I are locations. Here I'm taking at in locations a two-dimensional, but for all practical purposes, I mean, it doesn't have to be in two-dimensional. It can be something else as well. But anyway, and so this is, if we take a very pure example, so S of I is on a spatial grid 1, 2, 3 up to n, and 1, 2, 3 up to n. So that's north, south, east, west. And so these are all possible combinations. Let's say it doesn't have to be n and n, can be n1 and n2. And we will consider rescaled locations, x of I, that's my notation. So then once we have divided all these 1, 2, 3 up to n by n, then and 1, 2, 3 up to n here by n, then you have got your two-dimensional rescaled locations. And now that will be in 0 to 1, right, squared. So that's our regression model. Epsilon I is again epsilon of S at Si. That's the process, spatial process. Has 0 mean and let's say finite variance, being sigma squared, but it doesn't have to be constant because we are looking at very large scale. So there can be heterogeneity and there might be other moment conditions. So, and these mu, sigma are smooth functions, and we want to know what are the locations where, so very simple questions, where mu is larger or lower than a threshold. For example, the exceedance location where it's just roughly EL. So maybe you're testing the null hypothesis. Where is it lower than eta, or rather, where is it higher than some threshold eta? Or you may be interested in the other hypothesis, right? The other way, or not equal to whatever way you set up your hypothesis. So anyway. So what you want is to set up a test statistic, of course. So some estimate of mu, let's call it mu hat, and then subtract the true mean, divide by the standard deviation here, and here we are looking at bias corrected in case your estimate for mu is not unbiased. So that's the test statistic, and we want to see some kind of, critical value, if it's higher or lower than some critical value. So, suppose that asymptotic normality holds, so that's my notation. So when you're subtracting the mu, so that I write mu of x, and x is the location that's of interest. We want to know if at little x, on rescaled notation, if we have achieved an exceedance or not. So suppose that asymptotic normality holds, then you have some critical value z alpha, or minus z alpha, whatever your test alternative may be. And then you have, if that happens, if your null hypothesis is rejected, then x is your exceedance location. And first of all, let's talk about a little bit about estimation. Of course, this we are you can do it different ways. If you look at the Priestley-Chow type estimator, that's here at the bottom of the line page, mu hat of n. Then we have, let's say we take a product kernel, k. So essentially, you are taking weighted average of your observations in small neighborhoods. And so the weights are defined in terms of kernel and bandwidth. So it's a two-sided, so I'm taking a so-called product kernel. This is actually, you can take a bivariate probability density function, and we are taking product of two univariates. So a k is a symmetric univariate continuous probability density function on a compact interval, -1 to 1. And B is a bandwidth, which is very crucial, as we know, for bandwidth selection becomes an issue, and not so much the kernel. So bandwidths are essentially, these are converging to 0, but at a controlled rate. So, for instance, n times b to the power 3 goes to infinity, and there may be other conditions. So this is how it looks. So your regression estimator is a weighted average of your y values. These are y's are our responses. And in this case, you can work out the asymptotic bias and the variance terms. For instance, you can use the usual Taylor series expansion and to show that the bias is of the order, the leading term is of the order b squared, multiplied by some stuff here, and some then r1, n, so that's the of lower order, of less interest. And so the bias involves, of course, a second derivative of the unknown function that you're trying to estimate. Estimating bias, there are various prescriptions, works by Theo Gasser from University of Zurich, now retired, and his colleagues, for instance, Hans Müller, who is at the University of California in Davis. So they have worked out prescriptions for how to compute the bias, estimate the bias. Variance, if you had uncorrelated data, then you could work out the variance, and so variance would be, the leading term would be of the order 1 over nb squared. So there you know what kind of conditions you want to impose on your bandwidth so that the bias goes to 0 and the variance goes to 0, and consequently you would have weak consistency. If you had independent errors, then you can also work out when would we have actually the convergence to normal. Well, then you can just check your Lyapunov conditions by setting up these quantities here, which are independent if the errors are independent, but of course not identically distributed. And you can see that what you need is that the error should have, for instance, the third moment, a third absolute moment. Then you are okay. Then the central limit theorem will hold. In this case, what's the implication for the data? Just a quick look at the data. So this is the Alaska tree data. And what I've done here is that, so this is the x-axis is the longitudinal coordinates, y is the latitude, and the colored points, so the green ones, in my picture, green ones are thinner, red ones are thicker, and the black ones are in between. So these are the diameters of trees, of plot means. Okay, so this is a very large area. So these are forest plots on a grid, and so I'm taking average of the tree diameter values, and these are the plot means. So it's kind of flat, as you can see. The greens and the reds are all mixed up all across the landscape. And so that's the histogram, but it doesn't this one looks quite nice, but for the discussion, it doesn't have to be such a nice thing. So essentially what we are looking for are zones, if we can see some clusters. So if you just, here we are doing individually testing the locations. If you have alpha eta exceedance location, so meaning if your hypothesis is rejected at level alpha, where eta is your exceedance location, and if you sort of shift your threshold, here is the eta. If you shift your threshold, then you can see it's the exceedance locations are of course in that way. So anyway, so when you are entering this huge forest in Alaska, where are the thick trees? Well, it's kind of that way. So it's kind of northeast kind of. So here's more. Is more southeast, but generally in the eastern side. Okay. If we have correlated errors, so let's look at this, the same model again. So y is mu plus epsilon, and let's say the epsilons are some kind of unknown transformation of a latent Gaussian process. Okay, and the correlations in the Gaussian process z is going to be reflected upon the correlations in epsilon and hence in y. Okay, and so this g is a transformation that's unknown. This function is unknown, and L2, and possibly monotone, and it has got advantages. For example, g may be, if g is monotone, then for instance function, it's unknown, then the Hermit rank will be 1, and I'm going to talk about that. That has some advantages. So z is a latent, so it's not observed, of course, and g is unknown, so that's our error. Okay, so here are some references by Taku or Peter Meyer and Chorgo and so forth, papers by Milnichuk, and also book by Jan Beran has lots of discussions on this type of model. And so our correlations in the Z, so let's say that it is like so, that of interest may be isotropic random fields, and we are considering maybe short memory or long memory correlations. Let's come to this page. So our Z is on a it's a continuous index process, but observations are occurring on a grid. So short memory would mean, for instance, for some any M0, integer M0, this will be finite, sum of correlations over all lags. Whereas for long-range dependence would mean that the correlations decay slowly like so. Essentially, and in particular, it would mean that such a sum would be infinite. If G is monotone, as I was mentioning, then this its Hermit rank will be equal to 1. In any case, if M0, we take it to be M, then the long-range dependence in Z will be inherited by the errors. This can be shown by a little algebra. Anyway, so coming back to the errors one more time, let's take a closer look. So because we have a finite variance assumption, what we can do is that we can actually, this is the error here, so we can expand it using a Hermit polynomial expansion. All its components are unknown. M, the Hermit rank, is unknown, but if we assume that is monotone in Z, then M will be 1. But these are Hermit coefficients. They are unknown, but we assume them to be smooth. The HL, they are Hermit polynomials. They are orthogonal, which has advantages for computing variances. For instance, the variance of the error will be come out looking like this, which will be finite if we assume that the errors have finite variance. Now, the bias will be as before, look like this. The bias will not be affected because of some correlation in the data. Of course, it will still be of the order b squared, whereas the variance you can work out starting with this expression here, because where you plug in the Hermit polynomial expansion, and you can work it out that in case of short memory, the variance of your estimator of the surface will be of this order. So again, you know what kind of condition to impose on your bandwidth as a function of the in terms of the sample size, right? And so this is the short memory case, and in case of long memory, again, the variance will be of this order, that 1 over nb to the power 2m alpha, where alpha is a parameter. That's a long memory parameter that's coming in. So if that goes to infinity, then your variance also under long memory, it will go to 0. So then comes the question of consistency. Before we go to do other things, so pointwise consistency follows from Chebyshev's inequality. Of course, the mean squared error converges to 0. So the pointwise consistency follows. The uniform consistency, you can actually look at works by various other people like Silverman and so forth. Now here is another idea based on Parsons. So if you take a kernel that has got an absolutely integrable characteristic function on the whole real line, then the proof is actually very simple. By the way, this kernel, if you impose this condition, for instance, the uniform of the block kernel is out. Okay, that doesn't have that property. Okay, so which is very interesting. And anyway, truncated normal would have it. I'm talking truncated because I'm looking at it on a compact interval. But anyway, normal has it. And so on. So if you do that, then what happens is that to prove consistency, you look at mu hat, you write it down, that is a true mean, plus its bias, plus the remainder that came from the bias, plus comes this Sn term, which is essentially smoothing of the error. Okay, this is an identity. It's not approximately equal. So what you want to show is that the expected value of that quantity, supremum of the absolute Sn, converges to 0, right? And to do that, what you do is you write down your kernel using the inversion formula for characteristic functions, and then at some point when you take the absolute value and supremum, because this is e to the power ix, the x disappears instantly. And for instance, in the short memory case, it comes out very, very quickly that your condition then depends on the integral of the absolute value of the characteristic function. So your conditions come out there. So you know then under which conditions in short memory or long memory you would get infinite consistency. What that means is that because if you now define the residual, subtracting from your y the estimated mu, you've got the residual, essentially that means this identity holds. The difference between mu hat and mu is equal to difference between residual and your true error in absolute value, of course. So if the left-hand side converges to 0 uniformly and in probability, so does the right-hand side, meaning your residuals are close enough to the error so that you can work with them. In particular, as I was saying, Gasser, etc., Gasser and his collaborators have done good work on how to estimate the bias of non-parametric curve estimates. As far as the variance goes, in our case in particular, we have a very complicated situation because lots of unknown terms are coming in because of the correlations in the data. However, you can, because we have a situation that we have this function g, which is our errors are transformations of a Gaussian process. The Gaussian process is not observed, but there are these Hermite coefficients. If you impose regularity conditions on the Hermite coefficients, you can show that the covariance between epsilon I and epsilon j, the true errors, it's not covariance stationary. However, they are locally covariance stationary, meaning if you look at very, very small neighborhoods on your spatial grid, very small neighborhoods, you would get stationarity. So you can then impose, you can then plug that in. So then the question still remains, how do you estimate that locally stationary covariance function? And for that, you can directly use the geostatistics, so you can actually go via the you can use residuals because of the uniform consistency that we talked about, and you can do in small neighborhoods, you can do the variogram and the variance you can estimate. And to ensure that you are in small neighborhoods, you can of course impose kernels, and then you can plug that in back there. So this way you can actually directly estimate this G function without actually having to go through the correlation structure. So now, coming back to, for testing, of course, we will need, whether the exceedances occur, we will need limit theorems. So if you now go back to the mu hat, so mu plus bias plus this smoothed error, the R1n is missing. That's an error, another remainder that should have been, that converges to 0 anyway. How much time do I have? 6. Thank you. How to do the, so what do we do about the, what's happening to the limit theorem? The asymptotic distribution of your test statistic. That's what we're going to get at. And we jump to long memory right away. The short memory will be as we get similar results as for the uncorrelated independent case. So the long memory case. So we start off with mu hat is equal to mu plus its bias plus this bit that where you have smoothed the errors. And as I said, there is a little bit, I forgot to type that in. That's a smaller order anyway. So that doesn't matter. And now this guy here, we want to know what is that. Well, you can take the first term, that's the j from m to infinity. M is the Hermite rank, so that's the first term. And that is again the rest of the from m plus 1 to infinity. And the trick is to show that the larger part, the big sum, actually converges to 0. And using there you use Chebyshev, and then this bit here is that you want to look at what is the limiting distribution of this. Now, if m is equal to 1, you are looking at here Hermite polynomial of degree 1, that is z itself. So what you have here, if m is equal to 1, here you have a linear combination of normals, standard normals, and so that is how the central limit theorem for that, your test statistic that I had originally mentioned, that you take your mu hat, subtract your bias, the mu, divide by the standard deviation. That's how the central limit theorem will follow. And you get actually converges to normal 0, 1 if m is equal to 1. As for and this is my last slide, the multivariate central limit theorem. So if I now wanted to test for multiple locations, the result that you need is that if you take fixed locations, okay, then the covariance between the two will converge to 0, okay? And this means that if you now look at the multiple locations, then of course you can take a linear combination, right? Then you can do multivariate central limit theorem. And because of this result, then you have actually convergence to the multivariate standard normal. So this then can be used to test for a fixed set of exceedance locations, and that you can do many different ways how to calculate which threshold you will be using. You can manipulate your alpha using the results from this, and you can go via the if your p goes to infinity, then you can go via extreme value theory. There you can work out what your critical value should be. Otherwise, you can exactly for finite p, you can also do the usual algebra and get the critical value. Thank you. That's my talk.